Hello, this is Yoav Lavi, Philosophy Sixth Period, and here's my podcast. If you're listening to this, there's also, I'll probably submit an audio version as well as a video version, and I recommend you watch the video because I'm going to be showing some stuff, and I think it's just more helpful to kind of see it. But I'll try to structure this so that you can listen to this as well if you're insistent. But so my podcast is about the history of computing and just computing in general, really. So let's start with history of computing. What do we start with? First, computers, maybe manual computers. You can think of them, okay? And manual computers, what are they if not hands? And before you roll your eyes, I think this they do have some historical significance. Look up, bit, binary digit. Where do you think the digit comes from? Hands, right? Um, I guess this. I mean, and we elementary schoolers use hands as sort of calculators. It gives good intuition as into adding and subtracting. If you wanted to add 3 to 6, you could do it with your fingers and stuff, and for counting as well. And that was what the only thing we had for a while, just this 10 finger intuition. But very early societies like Babylon in 2000 BC, they started using what's called the abacus, and I have one of those right here. Um, it could be called also a computer, and Britannica itself, I mean, say does list this in its list in its history of computers. I mean, you can use this to calculate stuff, right? In a brief explanation, if you're listening to this, you should look up what an abacus is. It's like the thing, but yeah, each wire represents an order of magnitude, right? So there are 10 beads on each wire. The first wire is for the ones place, the second is for the tens place, the third is for the hundreds place, and so on and so forth. So you can count with this very easily. You just move all the beads, all the 10 beads over one by one, and then when you're out, just carry one on the next wire. So let's say I wanted to add 17 to 16, right? So first I would start with, I would write 16 on this abacus. So 1 in the tens place and 6 on the ones place. And then I add 17, so 1 in the tens place and then 7 in the ones place. So I count 1, 2, 3, 4, but then I'm out. I have to carry 1, bring all of them back. 5, 6, 7. And what am I left with? Well, I read what's on the abacus. So in the tens place I have 30, and in the ones place I have 3, so 33. All right. So that's basically how the abacus worked, and that's pretty much all I'm gonna say for manual computers. I mean, I don't know, but mainly our computers after that, what we used to calculate stuff had to exploited the use of gears. So we had the analog computers for the longest time. The first one, one could be the Antikythera, which was actually only discovered recently in the early 20th century. One of the people researching it, the physicist named Derce de Sola, calls it the first analog computer. What it was is the ancient Greeks had this machine which worked on with a lot of gears and dials and stuff, and it was basically a big astronomical calendar. When it was constructed, I think in like 200 BC, I think it could predict solar eclipses and lunar phases and stuff like that, and the star movement and solstices up to an accuracy of I think like at least 10 years. So pretty interesting. Thing is, the reason we didn't know about it till then, till last century, is because it was on a ship that headed toward I, but it crashed on the island called on the island of Antikythera, which is a Greek island, and yeah, so all the things aboard the ship were lost as well as that device. So that's that. Um, I'm gonna skip. Yeah, after the ancient Greeks, I mean, more there were calculators like similar calculators in the Islamic Golden Age. I can't name any, but I want to skip to the 1600s, which so Blaise Pascal created what's called created a calculator, which also again worked on gears, on metallic gears. It was considerably smaller than that Antikythera, but still pretty unwieldy. And it he created it for his father, who was a taxman. I forgot, but he had to do a lot of arithmetic with a lot of numbers manually. So he created it to maybe try and help him. And so yeah, he created that when he was 19 years old. But the device itself wasn't. It was very slow and not very useful. It was after he invented it. It was really more like an ostentation than anything. When people bought it, they never really used it, but they just showed that they had it. But really, I mean, it's a good start, right? For as far as like, and this is what a lot of people. The Pascalian is what is commonly regarded as the first calculator. Okay. Um, Now, oh yeah, and later that century, in the 1600s, the Gottfried Leibniz had his own had his own improvement on the Pascal line. But yeah, but we'll get back to Leibniz shortly. Then skipping to the early 19th century, in the 1800s, Charles Babbage um, created what is now called maybe the first computers, the actual computer, which again worked on dials, and it was very huge, but he created the difference engine. And the difference engine could calculate polynomials, which if I know you got up to that level of math, so you could see why polynomials are important. They not only for just polynomials, but you can approximate any type of function with polynomials, which is very important. And funny story. So he created that. It was huge. It was a massive thing. Um, but he wanted to create his analytical engine, but he didn't. He had the design for it, and it would be the first pretty like Turing complete general purpose computer, but he didn't have the funding from the British government, so he couldn't finish it. So basically, now skipping 100 years, we get to uh, um, the vacuum tubes. And what are vacuum tubes? So in basically in every war, it was good news for people who were thinking about computers, because they got a lot of funding. They could play with new toys, because the government uh, funded all kinds of computer research in order to get an edge in the military as far as calculating bullet missile trajectories and stuff like that. Uh, and in World War II, one of the devices that was used to calculate such things was the ENIAC, and the ENIAC worked on these bulb-like things, and I should draw them. And if you're listening to this, you should look. You should kind of look this up. But it's really hard to explain how exactly this works. But um, it was these bulb-like, light bulb-like things that were called vacuum tubes. And what they would do is, if you kind of turn it on, you can say, um, then it would let current pass through. I'll and I'll tell you shortly why that's important. But this is a good image to have of of what this does. When we turn it on, it lets current through. Okay, like electrons, right? It lets electrons through the wire right here. Um, okay, and the ENIAC, it had like 100 such light bulbs on each computer, I think, and all the radios. I think every radio in that time had one. But it was a great improvement on computers, on mechanical computers, but it it took a lot of power. It took a lot. You had to first. It took a lot of space to begin with. It was comparatively to today. It wasn't very reliable. That every like twice a day they had to replace some of these vacuum tubes because they would go out, just like light bulbs go out frequently. And so yeah, and they couldn't switch it on and off very very quickly, which was also a problem. So now we introduce the transistors, and the transistors work similarly to these vacuum tubes, but they are smaller. And they were invented by the first transistors were put forth by Bell Labs. Three people, I forgot their names, but Bell Labs. Um, and again, three main parts really. Uh, Now, really, it's hard to explain why transistors, how transistors work. I don't really understand it myself, but you should know that it works kind of like that other example. If you apply a voltage through this here gate, um, then it lets it lets it lets current through, it lets electrons through, and that's achieved because of the chemistry of a semiconductor, which exists in this layer here between the gate and the transistor, and it's usually silicon. And I don't know why my thing isn't writing. And silicon, that's the semiconductor. I think that was I forgot what year Bell Labs introduced this new technology, but in the they didn't completely replace those vacuum tubes until about the 60s, which was when the transistor revolution started, when the transistor count, the amount of transistors people could fit in a narrow space, that's the transistor count. So when it started really increasing was in the 60s. So people started switching to it because it was much more efficient. And so a lot of that revolution happened in California. And if you know, in that area in California, which is called Silicon Valley, it's named after the silicon, that semiconductor, which exists inside of that transistor. So anyway, Now, why is this important that you can turn on and off a transistor, right? Why is it important that when you turn it on, it lets current flow? And that's really a complicated question to ask, but I want to revert to a lot of ideas that maybe could explain this. So let's revert back to ancient Greece, right? You know, Aristotle created his, Aristotelian logic, term logic, right? And the important part is his propositions, okay? And propositions could be either true or false. Anyway, and there was a whole system of logic, all right? And then in the 1800s, a guy by the name of George Boole created, well, first of all, in the 1700s, Gottfried Leibniz said, put forth that maybe computation would be done best in a binary system, a system which used a binary number system, because it's really easy to implement. It's either 1 or 0, true or false. And so he kind of suggested that idea, and in the 1800s, George Boole, who is a mathematician, created what's now called Boolean algebra, where he put into mathematics Aristotle's logic. So now it's called Boolean logic. And that area of logic was largely unexplored. It was seen as just useless mathematics by most people. But then, in the late 1930s, I think it was, another guy by the name of Claude Shannon, came out with his master's thesis, which is probably the most quoted, the best master's thesis of all time, most cited. He introduced the idea that you could use Boolean logic. You could implement Boolean logic for computation with electricity gates, with the interaction of transistors, the transistors which I showed you earlier, and particularly, let's say you have an AND gate. If you have an AND gate and two inputs, right? So two wires going into an AND gate, and maybe I should draw this. An AND gate, maybe I'll say like this, like a statement. It's either true. So if you have two currents or two propositions, right? One of them is true, so 1. The other one is 1. That's the only case in which it outputs 1 as the output, right? But if either one of them is false, let's say 1 is 0, then it too outputs 0. Okay. So that's what he put forth. He said that you can use Boolean logic, and you can implement Boolean logic with logic gates and with electricity to do computation. And so and he invented the bit that that you can use it like a strings of these bits to compute information and to store information. Okay, so I just wanted to call his name because that's important. And so that's how computation kind of works with Boolean logic gates, which ultimately were kind of influenced by Aristotle. So now, so there was the '60s, then transistor count, the amount of transistors per unit area, followed Moore's law. George Moore was one of the founders of Intel, but he observed once that every couple of years, the um, the uh, the transistor count doubles. So every year they manage to fit them to pack them within tighter space. So they can. So that means more storage capacity and faster computation. So your whatever it is computes faster. And it's been true pretty much up to today. For example, like you strike me as an iPhone person. So let's say you got your iPhone like I don't know 4 years ago. Okay, um, and your iPhone probably has like I don't know like a billion transistors. If you bought another iPhone now, it might have 2 billion transistors in your phone. So that's every 2 years they manage to do incredible um, increases. But it seems like they're kind of plateauing now, and I asked my dad about this, who works on this, and he told me what they're going to try to do now is that you can't make them any closer on this dimension. So what they might try to do, um, computer chip companies, is to kind of stack them on top of each other, and that could be the next thing. But other than that, we've pretty much exploited fully transistors. So what now? Uh, and this is where I want to talk about what I like. So quantum computers. So I talked about the vacuum tubes and the transistors. So now skipping over to quantum computers. This is a proposed, still theoretical, but proposed new way of computation. This and physicists are still working on the actual like physical implementations of quantum computing. But I'll tell you why I think it's cool and important. It could do a lot of tasks that modern computers working on semiconductors can't currently do. One of them is the most famous one is factoring composite numbers. So again, right? So factoring means like finding like prime factorization is maybe if I wanted to find the prime factors of 15, 1, 5, then the factors of 15 are prime factors are 5 and 3. Okay, and I wrote them horribly, but anyway, you get the point. In modern encryption schemes, use the RSA encryption. Bitcoin uses it, and most online encryption schemes, and they work on the fact that factoring large numbers is just unfeasible for computers. Factoring a 256-bit number is not within the realm of modern computers working on transistors. So this is where quantum computers come into play, because where um, classical computers, modern computers can do it in exponential time. That is, as the number to factor increases, the time to factor it increases exponentially. A quantum computer can do it in polynomial time, which means it doesn't increase as much. So it's still pretty reasonable, and you don't have to wait more than the universe has time to factor large numbers with the quantum computing. Theoretically, again, there are no there are not yet have been like successful quantum computers. But yeah. So and another thing they can do, which is actually really important, is they can solve non-linear differential equations. And I know you might know what differential equations are. One of them I talked about in my last thing, which is the Navier-Stokes equations. Um, and a quantum computer might be able to solve those. And just recently, I read there have been two independent studies that came out by MIT and our very own UMD by Andrew Childs, who figured out quantum algorithms to solve nonlinear differential equations, which can be really important because they model a lot of movement, fluid movement. Like the Navier-Stokes equations, they model air movement and water movement, which is very unpredictable right now. And for example, we can only get climate weather predictions for an accuracy of up to 7 days. Other than that, it's we can't really. So if we ever get quantum computers, um, they could figure out the climate for a high, like more days of accuracy. And so that's one. So these are two advantages of quantum computing. So what is it actually? Well, I've said before that the units of computation in our classical computers right now is ones and zeros, the transistors which either turn on or off, true or false, one or zero. Quantum computers, on the other hand, their units of computation are what are called the qubits, see, quantum bits. Um, they are not. They don't necessarily have to be true or false. Rather, they are in a vector addition of the one state and the zero state. And it's the advantage that this poses is not immediately obvious, but mathematically they've proved that if you had such a computer that can be in a superposition of the one and zero state, that it can do a lot of computation really really quickly. Um, and so that's basically what a quantum computer is. So I just thought that was interesting. It could do a lot of cool stuff. And yeah, so that's the podcast.